when it comes to email security, end-to-end encryption stands at the top of the ladder. It guarantees that only the sender and the intended recipient can read the message, no one else. Not even your email service provider. Unlike TLS, which only protects emails while they're in transit between servers, end-to-end encryption covers your message from the moment you hit send to the moment it's read. Even if a server gets compromised, your email stays protected. This powerful architecture helps tackle serious risks like man-in-the-middle attacks, data breaches, and unauthorized access. It's also a big win for compliance, helping organizations meet regulations like GDPR, HIPAA, and SOX while keeping sensitive conversations private. Core architecture components. Let's break down the main building blocks of an end-to-end email encryption system. 1. Cryptographic foundation. At the heart of the system is hybrid cryptography, a combination of symmetric and asymmetric encryption. Here's how it works. Symmetric encryption, often AES 256, handles the actual message content because it's fast and secure. Asymmetric encryption, such as RSA 4096 or elliptic curve cryptography (ECC), is used to exchange keys and create digital signatures. For future threats, especially from quantum computing, some systems are now integrating post-quantum algorithms like Crystal's Kyber and Crystal's Dilithium. And to stay flexible, the architecture is designed to easily switch between algorithms without disrupting ongoing communication. 2. Key management infrastructure. This is the backbone of the system. Each user has a key pair, a public key, and a private key. The private key stays safely on the user's device. The public key? That gets shared using systems like PKI or a web of trust. In corporate environments, key escrow mechanisms might be used. That means there's a way to recover encrypted data, but only with strict controls. Techniques like Shamir's secret sharing or threshold cryptography are used to split and protect keys. To prevent attacks, public key directories and certificate transparency logs are used. The system also includes key rotation policies, meaning new keys are created regularly, but older messages remain readable. 3. Message processing pipeline. It all starts when you write a message. A unique symmetric session key is generated for that message. This key encrypts the message using secure methods like AES-GCM or CHA-CHA-20, Poly 1305. Even metadata like the subject line and timestamps can be encrypted to hide sensitive info. Then comes the digital signature. The sender signs the message with their private key. This proves it really came from them and that the message wasn't tampered with. In high-security environments, multiple signatures can even be required for a single message. System design principles. 1. Scalability. End-to-end systems must work for millions of users without slowing down. Here's how they do it. Distributed key servers manage public keys at scale. Load balancing spreads the work across multiple servers. GPU acceleration speeds up heavy encryption tasks. Caching helps with frequently accessed keys to reduce load times. Larger organizations may split users across domains but still support secure communication across those domains. 2. Interoperability. In the real world, not everyone uses the same encryption standards. That's why this architecture supports OpenPGP, SMIME, and even proprietary formats. If the systems on both sides don't match, the architecture can negotiate the best supported protocol or even translate between formats automatically. There are fallback mechanisms too for when encryption isn't supported by older systems. 3. Security controls. It's not just about encryption, it's about total protection. Private keys are stored using HSMs, TPMs, or secure enclaves. Zero-knowledge proofs can verify identities without revealing secrets. Multi-factor authentication, like biometrics or hardware tokens, adds extra protection for accessing keys. And finally, audit logs and automated threat detection help monitor suspicious activity in real time. Key exchange mechanisms. 1. Asymmetric key exchange. The system uses elliptic curve Diffie-Hellman, especially the curve 25519 variant, which is fast, efficient, and secure. To prevent man-in-the-middle attacks, protocols like station-to-station add authentication using digital signatures. Some advanced systems even use the Signal protocol, which adds forward secrecy and protection even after a device is compromised. 2. Pre-shared keys, PSK. For ultra-secure setups, pre-shared keys are used. These can be shared offline through QR codes, USB tokens, or even voice confirmation. The system uses powerful algorithms like PBKDF2, SCRYPT, or Argon2 to convert passwords into strong cryptographic keys. 3. Quantum-resistant exchange. To prepare for quantum computing threats, some systems are already implementing hybrid models, combining today's encryption with post-quantum algorithms. Protocols like Crystal Kyber help establish secure connections, and some even explore quantum key distribution, though that's still mostly experimental and requires specialized infrastructure. Forward secrecy implementation. Forward secrecy ensures that even if your private keys are compromised, past messages remain safe. How does this work? For every session, the system creates a temporary or ephemeral key pair, generated with strong randomness from hardware and system entropy sources. Using the double ratchet algorithm, it continuously updates these keys, providing both forward and future secrecy. And when a key is no longer needed, it's securely erased, with policies that delete keys automatically and memory protections that defend against cold boot attacks or memory dumps. Session key management. Session keys are organized in hierarchies derived from master keys using cryptographic functions. These keys are rotated automatically based on time intervals, message volume, or specific security events. Key updates happen in the background so users aren't disrupted. And even if a device goes offline, pre-generated key material ensures seamless recovery and continued forward secrecy. Secure key deletion. When it's time to delete keys, the system doesn't just hit delete. It overwrites key data multiple times with random information, making forensic recovery impossible. Keys in memory are also protected during runtime. Special allocation methods prevent them from being written to disk, and tools like canary values or guard pages defend against memory corruption attacks. In high-security environments, hardware modules like TPMs or HSMs store keys securely and perform cryptographic tasks without ever exposing the keys to software. Advanced security features. Let's talk about the extras that make the system nearly bulletproof. 1. Metadata protection. Even if the message is encrypted, headers like the subject, sender, or recipient can leak sensitive information. That's why modern architectures encrypt metadata too, using format-preserving encryption to keep compatibility intact. To go even further, the system randomizes message lengths, adds fake messages, and introduces delays, all to obscure patterns. Some go as far as routing emails through Tor or mixnets, using onion routing to completely hide sender and recipient identities. 2. Anti-replay protection. Imagine an attacker resending your old email to trick someone. Replay protection stops that. Each message gets a unique nonce or timestamp. Sequence numbers detect duplicates or missing messages. And for strong verification, recipients might be required to send a cryptographically signed acknowledgement. It's like having a built-in bouncer checking IDs at the door. 3. Compromise recovery. Even if a key is compromised, the system can bounce back. It uses key healing, generating fresh cryptographic material not tied to the compromised keys. Detection systems monitor for anomalies like strange encryption patterns or suspicious key access and automatically respond by rotating keys or isolating systems. Out-of-band verification and multi-party key generation help rebuild trust between users after a breach. Implementation considerations. Building secure architecture isn't just about cryptography, it's also about design and usability. Client-side architecture. Clients use secure storage like OS key stores or dedicated hardware modules. Key operations are separated from message processing, often run in isolated environments for added safety. From a user perspective, encryption is seamless, but advanced users can still customize their settings. And if a device is lost, secure backup and recovery ensure encrypted messages aren't lost forever. Plugins help integrate end-to-end encryption with popular email apps so users don't need to switch platforms. Server-side components. On the server side, it's all about zero knowledge, meaning the server can't see your messages or keys. Servers relay messages, verify certificates, and manage directories without compromising your privacy. Distributed server setups improve reliability and use Byzantine fault-tolerant algorithms to maintain consistency even during attacks. APIs allow integration with existing infrastructure while maintaining all security standards. Performance optimization. End-to-end encryption doesn't have to slow you down, and here's why. 1. Cryptographic acceleration. Modern systems use hardware support like AES-NI or elliptic curve accelerators. Some even tap into GPUs for massive parallel encryption. Pre-computing frequent values, batching operations, and using processor-specific instructions help further boost performance. Public keys and certificates are cached to reduce repetitive work, and smart prefetching anticipates user actions. 2. Bandwidth optimization. Encrypted messages are compressed with entropy-safe algorithms, meaning they shrink without leaking clues about content. For updates, instead of sending entire messages again, only the changes are transmitted. Other tricks include header compression, efficient binary encoding, and streaming encryption for large messages. Adaptive quality of service adjusts encryption levels based on network conditions. Deployment strategies. 1. Enterprise integration. Businesses can integrate this architecture with their existing email platforms and directories. Centralized key management and role-based controls help IT teams enforce encryption policies. To stay compliant, audit logs track every action, and backup systems support disaster recovery without violating privacy. Redundant infrastructure ensures high availability even during outages. 2. Cloud service integration. In the cloud, confidential computing protects encryption tasks inside secure enclaves. Multi-cloud designs prevent vendor lock-in, and hybrid setups combine on-premises key storage with cloud-based message processing, giving you the best of both worlds. Secure cross-cloud communication keeps everything in sync. Compliance and legal considerations. Security must also meet regulatory expectations. 1. Data protection regulations. For GDPR, systems enforce privacy by design, giving users control over their data and consent. For HIPAA, extra safeguards like access logging, breach notification, and encrypted data storage are mandatory. In finance, regulations like SOX and PCI DSS require tight controls on key handling and audit logging, all of which are built into the system's compliance features. 2. Legal and jurisdictional issues. Encryption laws vary by country. The system uses geo-awareness to adjust algorithms and key sizes based on location. For lawful access, warrant-based key escrow systems can allow legal access without compromising the entire system. Everything is logged, ensuring transparency. Data sovereignty laws are enforced through automatic policy engines that adjust operations based on user location. Future developments. Let's look at where all this is heading. 1. Quantum-safe cryptography. The architecture already supports post-quantum algorithms, either standalone or in hybrid models. Although full deployment of quantum key distribution (QKD) is still limited to niche environments, the system is cryptographically agile, meaning it can switch algorithms as new standards emerge. 2. Artificial intelligence integration. AI analyzes message patterns to detect threats like phishing or key misuse. It also helps optimize key rotation and automate compliance reporting. Techniques like homomorphic encryption allow AI to work on encrypted data, meaning threat detection happens without breaking confidentiality. 3. Blockchain and distributed ledger integration. Blockchain brings tamper-proof key management. Distributed registries prevent impersonation, while smart contracts automate compliance and security responses. With consensus mechanisms like proof of stake, the system remains. Now, if you're ready to strengthen your cybersecurity skills and protect yourself online, I have a free resource for you. Download our free security checklist at Teleris.com. It's packed with simple, actionable steps to help you stay safe and build your knowledge. Want more personalized help? You can request a free consultation with our cybersecurity experts. Or if you're curious how Teleris works in real time, request for a demo to see how Teleris AI agents work. Now let's get back to the business of the day. End-to-end email encryption isn't just a privacy feature, it's a future-proof security framework. With its powerful combination of hybrid cryptography, forward secrecy, AI-driven automation, and quantum readiness, it protects your communications today and prepares you for the challenges of tomorrow. Don't forget to like, share, and subscribe if you've learned something new, and stay tuned for more content on secure systems, privacy tech, and digital resilience.